All right, folks, so we've done a lot of talking this chapter about Newton's laws and forces, and there's one concept that I want to circle around to and elaborate on a little bit more, and that is the concept of net force. So we established a basic definition of net force whenever we talked about our equation, F equals ma, because it's really F net equals ma. But let's elaborate a little more on a net force. The main point I want to make is that just because there's a force, it doesn't mean that there is an acceleration. There can be a balancing force. There are always multiple forces, not necessarily always, but there are commonly multiple forces acting on an object in any given situation. And the directions of all of them and how they interact, the interplay between these forces, is what makes these problems interesting. And it needs to be really stressed that it's not just one force that matters, that determines how something moves, but the combinations of all the forces on something, the net force. So take, for instance, an example of me standing here. I'm actually sitting down, but generally I'm standing in front of a classroom lecturing. So I've drawn myself over in the corner here, and I've drawn my curly hair like I like to do, and I'm standing on the floor. And we know, because I have mass and because I'm in a gravitational field, that there is a force of gravity acting upon me, that gravity is pulling me downwards. However, we know that I'm not accelerating downwards. I'm not accelerating downwards through the floor. So therefore, there must be another force at play. And in fact, there is, and we're going to label it as the normal force, because it's the force of the floor, and it's perpendicular to the floor. It's pointing upwards, gravity is pulling me downwards, and they balance. The net force is ultimately zero. And we can see that if we consider the equation. We know that if A is zero, well, we plug in A, m times 0, is 0. If A is 0, F net is 0. Well, F net is just the sum of all of our forces. Well, I can look at this simple picture I wrote here, and our forces are the normal force and the gravitational force. So F net should be Fn plus F sub g. Notice that I didn't make that minus F sub g. The sign information is inside of these labels. We just add the variables, the letters that we use to represent them, together. Inside that Fg might be a negative number, but Fg itself we just represent as positive. We have added all of our forces together. Well, we know F net equals 0, F net equals Fn plus Fg. Well, then 0 for F net must equal Fn plus Fg. And then we can solve for 1, say Fn, by subtracting the other to the other side. So we can see that Fn, the normal force, should equal the negative of the force of gravity. And that's where we would actually start to plug in numbers. If we plugged in our numbers for the force of gravity, well, it is downwards. It would be a negative number. We would have a negative negative, making a positive for F sub n, the normal force. Inside of these labels are where the real information is. And it would turn out that F sub g is negative. The number, the magnitude and direction would include a negative sign, while the magnitude and direction of the normal force would be positive. Well, I did something subtly in this problem without explaining it, and that was making this simple diagram. Now, this little thing I drew next to myself is a free body diagram. I represented me by just a single point, and then I labeled all of the forces that are acting upon me. A free body diagram is a simple representation of all of the forces that are acting on an object. So you make that object just a simple dot, and then you can start drawing arrows representing all of the forces acting on that object. And this is a nice quick way to visualize what forces are acting on an object and whether they will balance, or if there will be an if there will be an imbalance in the force. If it's balanced, there's no acceleration. But if there's an imbalance, there will be acceleration. And that really drives what's going to happen in the remainder of the problem. So let's look at a few simple examples of free body diagrams. So the simplest example is an object in free fall. If something's just flying through the air, there's only one force acting on it. And that force is gravity. So I've labeled it F sub g. Well, let's consider another common simple situation. An object resting on a surface, or just like the picture earlier of me standing on a surface. We know that that object is being pulled downward by gravity, but it's not accelerating, so there must be an upward force to balance it, which we're going to call a normal force, for a force perpendicular or normal to some surface. This object is not accelerating, while this one is. It's accelerating downwards because it has a net force, a leftover or unbalanced force in the downward direction. When the forces are balanced, there's no acceleration. Well, let's look at one last quick example. Let's think about pushing an object across a surface. Well, it's resting on the surface. Gravity is pulling it downwards, but it's not accelerating downwards. So there must be a normal force upwards. But we also know that this object is being pushed. So there's an applied force or a push force to the side. And if we look at this, we can see that there's balance in the vertical direction, or the y direction. So it's not accelerating up and down, but there is an imbalance in the x direction. There's leftover force, or a net force, in the right direction. And so there would be an acceleration from that net force. We'll take a closer look at free body diagrams in the lab this week and get a much better understanding of them. Or if we don't cover it in lab, some semesters I might just hand out a worksheet or give you guys an interactive activity online to do to get a little more familiar with free body diagrams. They're an incredibly useful tool, and I strongly encourage you guys to draw them at the beginning of every problem in this chapter. So let's talk a little bit more about balanced forces. So if we have balanced forces, like earlier we saw that, well, the acceleration was 0, so the net force must be 0. It goes the other way around too. If you look at your free body diagram and you see that the force is balanced, that means that F net is 0. Well, and if F net is 0, then the acceleration must be 0. And we can actually take that a step further. If the acceleration is 0, that means the velocity does not change, or that the velocity is constant. And these three facts go hand in hand, and each implies the others immediately. If something is traveling at a constant velocity, well, that means it has an acceleration of 0. It also means that there must be no net force, that the net force is 0. If instead you're told the acceleration is 0, well, that means its velocity isn't changing, and it means that the net force must be 0. Or lastly, if the net force you find to be 0, well, that means that the acceleration is 0 and that the velocity is not changing. Any one of these three things immediately implies the other two. So if you have one of them, you have all three of them. Now let's talk about the two situations in which velocity can be constant. If the net force is 0, we often refer to that as equilibrium. There's no leftover forces. And there's two types of equilibrium. Static equilibrium, where an object's not moving, or dynamic equilibrium, where an object is moving. So in static equilibrium, it means that an object is at rest, and it will remain at rest, because F net is equal to 0. Similarly, in dynamic equilibrium, if an object is in motion, it will remain in motion in a straight line. That is, its velocity is not changing direction or speed, and that the net force is 0. This is Newton's first law coming back again. An object at rest remains at rest, an object in motion remains in motion, unless there is a net force. If there's a net force, then those things do not hold true. But when the net force is 0, an object at rest will remain at rest, and an object in motion will still remain in motion. And this is sneaky. Because oftentimes you want to think that just because something is moving, something must be pushing it along. But that's not the case. Once something's moving, it will continue to move unless acted upon by an outside force. Typically, there's going to be friction and drag, and eventually something will slow down. True equilibrium is hard to find. But we will sort of work in our physics bubble in this theoretical land without friction. And for that, we're going to have a net force of 0 quite often. It's hard to come by in real life, but on paper we can make it work. All right, well that covers our physics lectures. So we now have all the tools in our tool belt to work problems from Chapter 3. So now we will move on and look at some examples. Take care, everyone.